बिस्मिल्लाहिर्रहमानिर्रहीम। हाँ जी, हमें से आवाज़ आ रही है?
अस्सलाम वालेकुम सर। जी सर, आवाज़ आ रही है।
यस सर, आ रही है आवाज़।
If you could remember, in the last lecture, we were doing this important example 3.1, which was time diversity. First form of diversity that we had studied is actually time diversity, and time diversity was utilized in 2 and 2.5G standards. So we were trying to understand this example. So just as a revision, because we had studied first two paragraphs of this example, just for revision, that in 2G or in GSM system, everyone can hear my sound and audio and video both?
Yes sir.
All right. So you had two bands. One was for uplink, other was for downlink. Each band was 25 megahertz. Now each uplink or downlink band of 25 megahertz was divided into 200 kilohertz subchannel. And each subchannel is actually shared by 8 users in a time division fashion, which means that one user will be given 200 kilohertz for some time. Then for the next time, the second user will be given 200 kilohertz. So you have FDMA, frequency division, duplex, and then at the same time you have time division multiple access. Now the user had slots of 577. Each user has a slot of, and for this much time, 577 microsecond, he will get the whole 200 kilohertz channel. Now, so when he will get one slot, then the second user will get, third user, fourth user. So if you multiply 577 by 8, you will get 4.615. So one frame was of length of 4.615. So this was written 1 kilo, 200 kilo. 200 kilo is switched between these 8 users, and total frame length you saw was in 4.6 milliseconds, while each slot was about 577 microseconds. Now what was sent? So in 2G we don't add video, we mostly had these voice channels. So voice is encoded by a speech encoder into frame lengths of 20 milliseconds. So we have speech frames of 20 milliseconds for each user. All right. Now, then the bits in each speech frame are encoded by a convolution code of rate half. What is the meaning of half? I told you, means one input then two outputs. So two outputs are given by these generator polynomials, and you can write these generator polynomials in terms of their functions. Okay, I think you can write them. We have also discussed that. So you're getting two outputs for one input. So the number of coded bits for each speech frame is 456. So once they are coded by convolution encoder, so a speech encoder 20 milliseconds becomes a speech frame or 456 bits. 456 bits. So 20 milliseconds they become 456 bits. All right. Now what happens? These 456 bits, they are interleaved. For example, the first bit, the 8th bit and 448 bit, they will go into the first time slot of the first user. The next bits, they will go into the second time slot of the first user, and so on and so forth. So after every 4.615, the second, after the other slot will appear for the first user or for any user. For example, this is 1/8, so on and so forth. They are fed into the first frame first slot. Now this starts the second frame first slot. So the second frame first slot, the second bit, and then the 9th bit, they will be inserted here, and so on and so forth. So this means that from the first to the 8th bit, to the next which is coming in the 9th bit, you have actually 8 slot time interval. All right. So since one slot occurs after this translates into roughly 40 milliseconds a delay judged. So I will show how this 40 comes. Okay. And first let us see that, so that there is no problem. As you can see here, so we had 8 users. Total frame comes out to be this thing. These are the 8. This is a total time frame, and a slot of each user is visible. So now what to feed in these slots? Speech frames of 20 milliseconds. They are coded. They become half. They become double. Their length become 456. 456 are interleaved in 8 different time slots of the in 8 different time slots or different frames. So it will have 57 bits. You can see here. Yes. So the next time slot for the first user will appear after 4.6, because 4.615 was the length of one frame. The second slot will be in the first, for the first user, the second slot will be the first slot of the second time frame, which will come after 4.615. The total number of slots will be 8 into 4.5. This is 33, which is approximately equal to 40 milliseconds. Right. So your 20 milliseconds. Now coming back to the lecture, you can see. So the 8 time slots are shared between 220 speech frames. Right. So you can see that there are 8 time slots, which have actually now become roughly approximately 40. With a rough delay of 40 milliseconds. They will be shared between 220 milliseconds speech frames. So one frame will become 40 milliseconds, and it will be shared with in this manner among the 8 users and all that. Then the next 20 will come. So between any 20, you have a 20 which has been converted into a 40 milliseconds, 8 time slots. So this is the interleaving structure. So what is the diversity gain? Okay, so you can see that the diversity gain is the maximum possible diversity gain is actually 8. This you can observe because the bit that was the second bit or the second bit, then you can see that the 9th bits from 0 to 7 once, then from 9th 1/9, and so on and so forth, that came at a distance of 8. All right, because you can see that one slot of user had 8 bits. So next was coming here. So distance between this one and this one was 8 bits. So it was coming after 8 time slots or 8 bits. So you can see all right. Then the next will come here, next will come here, next will come here, next will come. So we will, if we make sure that the coherence time of the channel, okay, we will see also details in a while. Coherence time of the channel is actually somehow less than the time frame. Then you can see in the next time frame when the next bit comes, it will be in a different channel because it is above the coherence time, greater than the coherence time. The second frame is coming. So your whole speech is actually encoded into 8 different time frames, and each time frame, if we choose intelligently, is coming in a different coherence time, or at a time where a channel is different. So when a channel is different, which means H are different, and hence we have full diversity gain of H, or SNR to the power 8 will be obtained. But actual, it depends on how the channel is changing. We will see this detail in a while. For example, if the mobile is moving with v velocity, then the largest possible droplet spread is equal to this thing. All right, I will tell you. From that droplet spread, you can find the coherence time. Okay. From the coherence time, we know we need the coherence time approximately 5 milliseconds or 4 milliseconds. We can calculate the speed required of the car. So even if the car is moving with this much speed, you will be getting a channel changing at this much coherence time, and hence you will be getting diverse channels with full diversity gain. Let us see its mathematics. So you can see here we have learned that this is the droplet spread. All right, carrier frequency, velocity of car, so on and so forth. And this was a coherence time, assuming that pi by 2 is significant. You feed this value, the coherence time comes out to be this. Now we need the coherence time to be less than 5 milliseconds. We know it is actually 4 points, as you just saw in our example. It is not actually 5, it is 4 points. 6.5, but let us just assume that it is 5, just for rough approximate, but you can use 4.615, no problem. So coherence time has to be less than 4.65 or 5. Let us assume 5 milliseconds. So coherence time has to be less than this. All right, but this is the coherence time formula. So you order this, okay? 5 milliseconds come here, 5 has to be greater than this. V comes here, 5 comes there. So V has to be greater than this, V greater than this, and you solve this. So V has to be greater than 12.5 meters per second, and you convert this into kilometer per hour. So for 5 milliseconds, actually it comes out to be 45 kilometers per hour. All right, but if you choose the exact value, you will get certain approximately about 30 kilometers per hour. Or whatever the case, whatever the value you choose, the car has to move with such velocity. Then only due to the droplet spread, the coherence time will be less than 5 milliseconds. Otherwise, then it will not be changing at such a fast speed, so that in the next time frame, the channel will not be different. This is what needs to be learned. Then he says, what will happen if I am moving 3 kilometers per hour? If we have a walking speed, we don't have a car, we are walking. Then in that case, the time diversity, you won't have that luxury because the coherence time will become very, very large. The channel is not changing at a very fast speed. It will become very, very large. So once it becomes, so we cannot use this type of diversity. So we move on to frequency diversity. So this is called the hopping mode. All right. So here what happens that all the slots of the 8 users, they can hop from 200 kilohertz to another 200 kilohertz. Okay. So we will make sure that it hops to a frequency which is greater than the coherence bandwidth. So the coherence bandwidth is with the typical delay spread of 1 microsecond, as we have seen in the table, is 500 kilohertz. So this you can also see actually. So if I just rotate this, so you can see here that if I have a time delay of 1 microsecond, then coherence bandwidth is given as follows, assuming pi by 2 to be significant, the phase shift. So if I just put the value, I can see that the coherence bandwidth comes out to be 500 kilohertz. All right. So okay. So if we jump to a frequency which is 500 kilohertz away, or 500 kilohertz, which is the coherence bandwidth, you will get another set of 200 kilohertz, which will be completely different from the previous channel. So again, you can get diversity. Okay. So total bandwidth for uplink downlink is 25 megahertz. So you have a huge bandwidth, 25,000 kilohertz. and you can get a lot of bandwidth away from the coherence bandwidth, where you can expect the channel to fade independently. So this section of time diversity is closed. So I will take a break and I will ask if anyone has any questions. Then we can move further. All right. Can everyone can hear me? Hello. Can everyone hear me?
Yes, sir.
Do you have any question up till this point?
No, sir.
All right. So we move to the next section. Now we will go to the next section, which is 3.3, and that is antenna diversity. Now, please see, up till this point, we have learned that if you want to have diversity, you have to send your signal or its replica in another coherence time. Maybe you are using repetition, or maybe you are using rotational, or whatever the codes. If you're using some coding, then again the next code has to be sent in an, or its copy has to be sent in a slot whose channel is different, as we saw in, for example, as we saw in rotational codes. Okay, with all the coding complexity and mathematics, you could see that the channel coefficients were different, H1, H2. So you have a code, but one symbol is sent in one slot and the other symbol is in another time slot, in such a way that these two slots have different channels. So they have to be sent in a different coherence time or after interval when the channel has changed. But many times we have a delay constraint or the coherence time is large. So it's so large coherence time that if you start waiting, you will lose the slot which you have. For example, if I want to talk and you have to listen, you will wait for me for some time. But if my next slot comes after a very long time, you will not be waiting for me. So you have these delay constraints. So what we will do in those channels where we have constraints with respect to coherence time or coherence time is very large. So other forms of diversity can be used. And here comes antenna or spatial diversity. This is obtained by placing multiple antennas at the transmitter or the receiver. And we try to make sure that the antennas are placed sufficiently far apart, very, very far away, that each antenna receives or has a channel coefficient that is fading independently from the other antenna. Hence, we have independent signal paths. So this separation will depend on the scattering environment. Near the ground, because we have, very much buildings and houses and cars. So the channel changes at very, very short distances. So we can have shorter spatial distances, half wavelength or lambda wavelength. But on high towers, we will require antenna to be separated on to several wavelengths. Normally 10 wavelengths might be required. Now there are two aspects if you are putting number of antennas. One is called receive diversity. This is called SIMO, which means single input, multiple output. So the transmitter is single, but you have multiple output antennas. So you have multiple antennas that are receiving the single signal. Other case is MISO, when you have multiple transmits and single output. So you can see SIMO is a very good example of uplink. So in this is in 3G, you have just one mobile, one antenna at your mobile, but at your base station you have several antennas. So it was a good example of SIMO. But for downlink, you have multiple antennas at the transmitter or at the antenna or the base station, but at the mobile you just had a single antenna. So this was a good case of MISO channels. So now actually we have started 3G. So now they become, this is not that difficult. We will see in a while, but a lot of work has been done, and we will see that they give rise to the famous space-time codes. Then the next is when you have multiple transmit and multiple receive on both the sides. Okay, so they become MIMO channels. So 4G has a constraint that all the channels must be MIMO. So only those mobile can shift to 4G. 4G compatible mobiles, which are a little bit more expensive. Why? Because they have to have MIMO in them. They have to have two antennas, at least two antennas at the receiver as well as the transmitter. So if the mobile is receiving, it must receive from two antennas. If it is transmitting, it must be able to transmit from at least two antennas. Base station always have more than two antennas. Two or more. Yes, please, I will stop. You can ask the question. Yes, any question you can ask.
जी सर 2 क्वेश्चन थे सर। पहले तो था हमारा जो पहले हमने भी बात की ना पीछे कि हमने एक कोहेरेंस टाइम में एक भेजी है बिट और उसके बाद दूसरे कोहेरेंस टाइम में दूसरा भेजी है। तो सर इसमें क्या गारंटी होगी कि जो दूसरा कोहेरेंस टाइम है वो ज़्यादा डीप फेड में नहीं था या दोनों में ही परफॉर्मेंस जो थी वो बुरी नहीं थी? यानी कि इसके लिए हम जस्ट कहते हैं कि वो दो सेपरेट अपार्ट हैं, दो डिफरेंट कोहेरेंस टाइम है, तो ये क्या गारंटीड है कि दूसरा कोहेरेंस टाइम बेटर ही होगा? सर एक क्वेश्चन तो
सर दूसरा क्वेश्चन भी answer one by please let us answer your question one by one. All right, okay, then we will come to your second question. No problem, we have a lot of time. Now please see, there is no guarantee that if the channel is very bad in the first coherence time, then the channel will be very good in the second coherence time. No, we cannot say that there is a guarantee. Remember, these are random processes. These are stochastic processes. They are always changing. So there is always a probabilistic dimension. So, but what we can say that yes, if the first is bad, then the second is totally uncorrelated with the first. Right? We have seen because of those, sine functions and all those. The second one is totally unrelated. So it is assumed that if it is one is not working, second will be working. Okay, but still we have no problem. All right, first is not. First was bad. Let us apply to second. All right, second let us apply to third, fourth, fifth. It will depend how many diversity branches you have. Okay, if you have 10 branches, and let us say 2 of them are not giving you that much of a single amplitude, but the rest of them they are giving you a lot of single amplitude, then you will still be getting a lot of diversity. Okay, so the main thing is that they have to be uncorrelated. Okay, this is not the thing that their amplitude has to be less or high. This is not the thing. If you could see, all of our derivation is based on the basic assumptions. If you try to go, in the back, actually, what was the starting point? This was the first error that we have devised. It was dependent on 2h square, and we said that, all right, what is the cause of this noise? So we said, even at high SNR, we are talking high SNR, what is the cause of the noise? What is the cause of the noise? The cause of the noise is that even at high SNR, there is a probability that h mod square SNR will be less than 1. All right. Or in other words, we can say that channel will be actually h mod square will be less than 1 over SNR, or channel will be in deep fade. This is all probabilistic. Okay. So, and we know its probability is also 1 over SNR. So we have done all the mathematics. Then for L branch it becomes to the power L, and then we have L diversity gain and all that. That is another discussion. But main point is that is totally dependent on a probabilistic model. Okay. So we are saying that as we have watched the channel, there is a probability that even at high SNR, the channel amplitude might be less. Okay, and a probability for this is this. Okay, and even for this type of channel condition, okay, we have seen that once we apply diversity, if you could see here, so we operated in the same manner, all right? Same manner we have operated. This, this mathematics was, the derivation was completely different, but finally, actually we had devised the same, thumbs rule or shorthand formula. Okay, that yes, again we can say that yes, h mod square is less than, this whole is less than 1 over SNR, and again the probability of this being less than R comes out to be 1 over SNR L. All right. So,
right, sir.
all right. So again, this is repeated in here. Here again, you can see, because there were two times you were sending the codes H1, H2. Okay. So again, you were mathematics is, but you can see these were two things. All right. Same way they were drive. So the meaning is that it is all probabilistic. Okay. The channel could be low or high. Okay, but we have talked about in terms of probability. Okay, even if it is less, it has to be less than 1 over SNR or 1 over SNR times L. Error is less than 1 over SNR times L. So probabilistically, this means you are getting L times gain because your error is less than 1 over SNR L. For same SNR, but if you have L branches, your error has decreased to 1 over L times probabilistically. Okay, so whatever the channel going up and down, but once you solve the channel with respect to its relevant statistics or stochastic process, you get to the same result that you are getting again. The channel is going into deep fade much less as compared to when there were no diversity branches. Okay. Now please ask the second question. I missed the second question. All right, what was your second question?
Sir, you have answered it. The second question was the uncorrelatedness between the two time slots that you have told. It's okay. अगर दोनों इंडिपेंडेंट होंगी तो दोनों की जो प्रोबेबिलिटी होगी उसको इंडिपेंडेंटली लिया जाएगा. तो अगर वो एक में फेड में होगा तो हो सकता है अगले में फेड में हो सकता है अगले में फेड में ना हो क्योंकि ये दोनों इंडिपेंडेंट हैं.
Yes. Both are independent. Okay, and they might be in fade, other might not be in fade. Okay, but they have to be. We try to send them because once if you send them, then you have diversity gain. If you send them in the same coherence time, you will not get any diversity gain because then the channel is same. And we want the channel to be different. That's the most important thing. It has to be multiplied with a different channel, H1 then H2. That is the main thing. So if the repetition code first symbol sent with H1, the first symbol repeated must be sent with H2, where H2 has to be completely uncorrelated with H1. This is the requirement. So we can move on to the lecture now. Any other question? So no question. We move further. Now, so I told you that for multiple antennas, single output or single input, multiple antennas, you have two cases. One is called received diversity. What is received diversity? So you have one antenna and you have multiple antennas at the receiver, one antenna at the transmitter. So most of the radar applications, are like this. So you have one antenna or one, aeroplane or one, target. But you have multiple antennas which are trying to get the target. Or in wireless communication, I told you, for 3G, it was actually uplink. So one transmit in L receive antennas. So, the channel model will be very, very simple. So, output is the same input, but let us say I repeat my input. I just send my input once, but L antennas will be receiving. Remember, all these L antennas, they will be present at a distance such that all the antennas have different channel coefficients, uncorrelated, independent. Again, their independence was in time. Here, independence is in space. So very good. You just send one symbol, but all the antennas have different channels. So all of them will be giving you different outputs, which will be uncorrelated with one another. Everyone will have its noise, but everyone will have a different channel. Yes, noise will be again, you know, n naught by 2, n naught by 2, Cn. We have said this many times. Okay? Noise is independent, we know. Okay? And so it is just like repetition code. Repetition code, you know, you send first symbol, then you repeat the first symbol, another H2, and you know you got an H mod gain, and all that mathematics you just saw, and you were getting diversity, you know, all that. If you could see, we had done this in the before the midterm. This is repetition code. All right, you are getting H mod. H mod square SNR. All right, this gives you a diversity, full-fledged diversity gain. All right, all that we have studied. Now, coming back, diversity gain of L. All right, so we will get the same thing as we got for repetition coding. Same, check the same equation, same equation. Now I can write this this term as product of two terms. One is L into SNR, while the other is written as 1 over L into H mod square. So I just, you know, rewrite it. I put an L here, then 1 over L, so it is actually the same. But what is it is actually showing me? Okay. The first thing he says, you can say this is a power gain. And the second thing we will see now is called the diversity gain. Now, what is a power gain? By having multiple receive antennas and coherent combining at the receiver. The effective total received signal power increases linearly with L. So you can see that if you have an H channel, all the H signal was stand H1, H2, H2. At the receiver, you know, coherent, we have, you know, coherent combining. So all the channel coefficients are known. So we combine H1 with H1 mod, H2 with H2 conjugate, I say H3 conjugate, all that. So you get this H mod square. So I divide this by L multiplied. So actually what is happening, your SNR has been multiplied by L times when you have placed L antennas. Now the second term is representing the diversity gain. Okay. And if you sum up average over the multiple independent paths, the overall is small will be decreased. The same diversity gain, because now remember that probability of all of them falling will be very small. You know, 1 over SNR times L to the power L. So because of this, so many L branches, or its length is L. Okay, so your probability of getting less diversity gain has decreased. Yeah. So we SNR that we have just discussed in a while, because it is 1 over SNRL. Okay. Even if all the channels are correlated, oh, very important point. If I say all the Foley channels are correlated, so let us say they are all same. They are all same. Yes, you know, diversity gain, we will not get diversity gain. Yes, we cannot get diversity, but diversity gain has to have channel coefficients. They have to be different. They have to be constant. But what about the first term? We will still get the first term. We will still get L times the SNR. The power gain will be still there. Only get power gain. Yes, you will not get diversity gain as we increase L, because how can we get? Because we are using correlated fades. Achha. On the other hand, if I say that no, the HFL are independent. Yes, and in that gain, all right, I will be getting a diversity gain. Okay, so and the power gain will be still there. Okay, So I will have a diversity gain as well as a power gain. So because this will be there.
एक क्वेश्चन है यहाँ पे भी।
Yes, आप पूछें।
सर क्वेश्चन ये है कि पिछली डाइवर्सिटी स्कीम में तो अंडरस्टैंडिंग हो रही थी कि हमने उसमें कोहेरेंस टाइम रखा हुआ था ना, तो वो दोनों अनकोरिलेटेड थे। अब इसमें हमने नई डाइवर्सिटी स्कीम में मल्टीपल एंटेनाज लगाए हैं। अब मल्टीपल एंटेनाज लगाए हैं, लेकिन वो जो फिजिकली जो स्पेस है वो तो सेम रही है ट्रांसमीटर और रिसीवर के दरमियान, जहाँ से इंटरफेरेंस आ रिफ्लेक्शंस आ रही हैं वगैरह वगैरह। तो पहले हमने कहा जी कि ये अनकोरिलेटेड है, और फिर हमने यहाँ पे अभी बात की है कि अगर ये कोरिलेटेड भी हों तब भी हमें पावर गेन मिलेगा और डाइवर्सिटी गेन नहीं मिलेगा। तो सर ये दोनों डिफरेंस कैसे बनेगा कि कब ये कोरिलेटेड होंगे और कब ये अनकोरिलेटेड होंगे? क्योंकि सर ये थोड़ा समझने में थोड़ा सा वो थोड़ी सी कंफ्यूजन हो रही है कि हमने सिर्फ एंटेनाज बढ़ाए हैं, तो हम ये कैसे कह सकते हैं कि चैनल चेंज हो रहा है हर एंटेना के लिए? चैनल तो वैसे ही नहीं है सर जैसा पहले था।
Yes.
अगर एंटेना आसपास होंगे तो सिमिलर चैनल मिलेगा उनको, ये एंटेना टाइप सेम होंगी तो सिमिलर चैनल मिलेगा।
लेकिन remember, we are actually trying to discuss all the possibilities here. ठीक है? Actually, it will all depend on the channel and the scattering environment. So mostly, if you keep, your antennas 10 lambda away, you will be getting uncorrelated fading. But let us say I place them at lambda by 2. Okay. So let us say I place them in a very adverse condition, difficult condition, or in a very highly populated buildings, and for example, I don't know, an Arcali, okay, na? Or very busy road, McLeod Road, whatever, okay, very populated, very much building and cars and all that. So in that case, even it might happen that at lambda by 2 you are getting uncorrelated fades. But let us say I place the same antenna with lambda by 2 in a thinly populated area with very few buildings, let us say in a village, and so that the same antenna might be giving me totally correlated fades. All right, so because there are no reflections, single path is there, so all the antennas might be getting the same type of channel coefficient. All right, so we are just discussing that in case of SIMO, when you have multiple antennas at the receiver, okay, then actually it can work for all the scenarios. Even when you are getting correlated or uncorrelated fades, you will be getting the gain. For uncorrelated, you will be getting an additional diversity gain. But for correlated, you will be just getting the power gain. Actually, it is also called the beam forming gain. Actually, जो आपके जो satellites वगैरह में भी ना, if you could remember, actually you have these gains, beam forming gain. Channel just multiply with their conjugates and you get the full-fledged gain. Because there you don't study diversity in detail. When making a satellite link, communication link, if you have multiple antennas, you just go up to this gain, power gain. But as in communication, we have a very, very difficult environment and so many users and a very small bandwidth which has to be allocated to so much. So there is quite difficult. So here we have to try to invent other gains. All right. So this it was an explanation. Channels might change. We are seeing the advantage. Advantage is that for SIMO, you will be getting double gain. Okay, or you will be getting single gain, but you are getting gain. Okay, which is not possible for other types of system. Now let us move on and go to transmit diversity space-time codes. So SIMO is very easy. One antenna, multiple antennas getting output, and you are getting a lot of gain. But the vice versa is not true. And my PhD actually also was on this in 3G. It was on MISO channels. Okay. Now they are quite difficult. The problem is that you have L transmit antennas, but you have one receive antenna. For example, a downlink. Remember, downlink always requires large bandwidth because most of the time you are downloading. So you have L transmit antennas at your base station, only one receive antenna. And all that you can see from industry point of view. You can see here. Now, how can I get my diversity gain? One way is simple. You say, all right, no problem. I use repetition code in a way that I just send one symbol through one antenna. All right. Then I use the same symbol and I sent it onto the second antenna. Okay. Simply transmit the same symbol. The L different antennas used during L symbol times. So you will first symbol, first antenna. All right. First symbol, second antenna, second time slot. All right. Third symbol, first symbol, third antenna, third time slot. Your third symbol time. All right. So look at what is happening. As you are sending one symbol through your L antennas, and you know all the L antennas are placed spatially apart, so they all have different channels. So you can see that all the symbols that will be coming to your one receiver, they will be all uncorrelated because they are being sent through antennas which are at spatially different places. This is actually symbol repetition code. You are just repeating the first symbol through so many antennas, but you can see it is quite wasteful, lot of waste. Why? Because you are wasting a lot of time. So when you send the first symbol in the first time slot in the first antenna, and then you send the first symbol in the second antenna in the second time slot, and so on and so forth. Now all the slots for the first antenna are empty until and unless you have repeated the first symbol L times. Similarly, in the second antenna, all the slots are empty. Only one slot has been occupied. So it is quite wasteful. Okay. As repetition code was wasteful, so we invented a new code, rotational coding, which was able to utilize. Here we will also try to utilize different things. Similarly, you can also use any code, any time diversity code. So, we have different codes which interleave. For example, you have convolution code, block codes. We interleave the bits, and by interleaving, so the same information across multiple slots, you can get, let us say, time diversity gain of 8 and so on and so forth. So you can use time block codes or convolution codes, and they can also be used here. But remember that one antenna again at one time will transmit one coded symbol, and then the same coded symbol will go to the second antenna in the second symbol time. Again, you will have a lot of you will get a coding gain also because you are using your codes. You will have diversity code, but again it will be quite wasteful. Degrees of freedom will be wasted, time will be wasted, space will be wasted. So a lot of research has been done in this area under the heading of space-time coding. We want to devise special efficient codes in space and time. Previously they were just time, now they are space and time. So a lot of work has been done. We will discuss the simplest and yet one of the most elegant, and that is called the space-time code, or this is also called the LMOT space-time code, the LMOT scheme. So it is actually, this is a standard for 3G mobiles. Most of the mobiles that are 3G, they are using LMOT scheme, or different variants of the LMOT scheme. So it is actually devised for 2 transmitter antennas, but it can be generalized to 2 or more than 2 antennas to some extent. Let's try to study the space-time codes. The LMOT scheme, the very famous LMOT scheme. Now, assume that I have flat fading, no frequency selective fading, simply flat fading. So, I have 2 transmit antennas. I have single receive channel. This is single receive channel is getting a first symbol from first channel, but a new second symbol has been sent to the second channel at the same mth time slot or same symbol time. So one receiver is getting 2 outputs from two antennas. So if I could show you the figure, yes, here, this like this. So this is one receiver, it is getting the outputs of both the receivers. So if x1 is sent, x2 is sent, this is h1, h2. This will be h1, x1, this will be h2 times x2 received at the receiver. That's the noise. So for notation, I say this is x1 sent from symbol antenna 1, h1 antenna of channel of antenna 1, channel of antenna 2, symbol sent from channel from antenna 2. Now, this was the first time slot. Now, what will happen in the second time slot? Now, in the second time slot, what you will do? In the, what is x1? The first antenna, second symbol time. Alright, this was what? First antenna, first symbol time. Second antenna, first symbol time. Now, first antenna, second symbol time. You will be sending minus U2 conjugate. You will not send U1, you will send U2 conjugate. Exact conjugate of the second antenna. And in the second time slot, second antenna, you will be sending conjugate of U1. And if we assume that the channel remains constant over the two symbol times, so we will assume, because we have just sent the repetition, change repetition in the second symbol time, so we assume that in the two symbol times the channel remains constant. All right, so this means that h1 of 1 is equal to h1 of 2, and h2 of 1, second antenna of 1 time, is equal to second antenna second time slot. They are equal to h2 and they are equal to h1. Then we can write both the equations in this form. All right, so a lot of mathematics again, this book gems, and I don't want you to get confused. Let's see my notes if you're able to understand. So you can see first symbol, first antenna, second symbol, second antenna, first, all are in the first time slots. Now in the second time slot, what happens? In the first antenna, I now send U2 conjugate, while in the second antenna, I send U1 conjugate. And I again receive the second symbol at the output of my antenna. So you can write this in this matrix fashion. You can see here, this is the way that you have to write in exams or space-time codes, and now then this will move on to MIMO systems. So you have to learn. So time is represented as a column. The space is represented as rows. So if we have one time, this is the first symbol from first antenna. This is the symbol of time 1 from the second antenna. This is the second time slot. So second time slot, you have the whatever the sim. This is just general, not of LMOD, it's general notation. So in second time slot, this is the first antenna. Second time slot, this is the second antenna. So antennas are in rows, and time is represented in columns. So now I can write my y1, y2 as h1, h2 times this, because h1 and 2 will go with u1, u2. So first antenna, first y1 will be equal to h1 u1 plus h2 u2, but second y2 will be equal to h1 into minus u2 conjugate and plus h2 into u1 conjugate plus noise. So you can see here, this will be the first h1 u1, h2 u2, this goes with this, and this will be the second, this goes with this. So these two plus these two noises, they will give me y1, y2. y1 and y2 will be equal to this one and this. All right, and here same equation, y1, y2 will give me. You can check same thing. You can similarly write y1 equation, you can similarly write y2 equation as I've done in my notes. So notes will be available as well as this recorded lecture is available. Now you can also take conjugate of the second equation. So no problem, I can take the conjugate. take the conjugates, whole conjugate, W2 conjugate, whole conjugate, this becomes conjugate conjugate, no conjugate, this becomes H2 conjugate, this comes here, this becomes U2, this becomes H1 conjugate, this becomes here. So again, you can write this in any form, Y2 conjugate, no problem. So again, you can write the matrix form Y1, Y2 conjugate like this, a little bit change, again like this, but they are the same equations. This is giving you Y2, this is giving you Y2 conjugate. Now in this equation, Alamuti found that there is a very nice mathematical property of matrices, and that is that these columns are actually orthogonal. They are independent. And you will say, how, sir? How can we show that they are independent? So again, moving on to my notes, you can very well see here. So you have this one. For example, you have this one, U1, U2 minus U2, this. And you can also write it like this one, H1, H2, H2, H2. Both are same forms, okay? But you can write, and you can see all of them are orthogonal. Let us check. So if I check this one, all right, I want to, if it was not a complex number, then how can you check orthogonality? So you multiply this with this. You make it a row and multiply with this column, it will give you 0, then it is independent. But if they are complex numbers, so you have to take its conjugate and multiply with this, right? It's no problem. I take its conjugate, multiply with this. So our conjugate becomes this, and multiply with this remains the same. Once I do the multiplication, you can see this becomes 0. So the columns are independent. If you multiply a column with itself, you will get full energy. U1 square, U1 square, right? If you multiply vector with itself, conjugate, if there's complex, then you will get the energy of the vector. Similarly, for H, you can see that if I multiply one column with the other, conjugate of one with the other, then you will again get a 0. But if you multiply it with itself, you will get the column and vector mod square. So we have shown that these are orthogonal. So this was realized by Alamuti. And once he realized that they have very strong orthogonality property of matrices, then he said, then there is no problem. I can utilize this property to get my output, okay, that will have a full-fledged diversity gain. Now, how can that be possible? So he said, no problem, use the same sufficient statistics as we have been using for repetition codes, okay, where we projected H or Y onto the other, or H Y onto other, or H onto, we will follow the general rule as established in this book. Whatever, you can project Y onto H or H onto Y, whatever the rule that has been established. So you project that, okay, and you solve, okay, and you see that you get this signal. All right. So if you project Y onto the first column, you will get R1 corresponding to U1, and if you project Y vector onto the second column, you will get R2, I2. So both R1 and R2, or U1 and U2, will be determined. Now, the book has missed all the mathematics, so I wanted to, actually I had done it, but then it was not that clear. So I tried to do it that every one of you could understand. So what is the sufficient status? We will follow the book. The rule has been established for, vector channels or vector inputs. They were first of all used in repetition code 3.33 equation. So there the established norm in our book is that you take H conjugate. H is a vector. H is a vector, repetition code H1, H2 up to HL. Here it is, let us say H1, H2. This is a vector. Take its conjugate. A vector conjugate means its transpose plus its Hermitian. You should understand. Vector conjugate means this. Multiply this with the output vector. All right, and then normalize this over its norm so that it is normalized. If you are getting high energy, it doesn't mean you are getting high energy. because you have to normalize this. This has been discussed many times. You can see in the last lecture. So we will just follow the old approach. So let us take H first column. I take the first column of H. I take its admission, multiply with Y, no problem. Okay. I can use any of the equations. So the equation used in the research paper of Alan Moody standard, he has used this Y. So this 3.75 equation, this one, this Y, this 3.75, or he has used this Y. So we will use this Y, no problem, because it gives us a nice form. So I use this Y of 3.75 equation, no problem. Simultaneous equation has two columns of H, so I use the first column of H. All right, I take its admission, but below I have to take, not mod square but under root. So I have to put under root H into H, because H under will give you H mod square vector, and its under root will give you square cancels H mod. Everything is according to rules here. Let's try to multiply. So I just, Hermitian makes it a row, and again a conjugate. This becomes conjugate, cancels. I multiply, go with this. It goes like this. Below, same thing happens, but it will go like this. So I put the value of y1, I put the value of y2 in the subsequent equations, the previous equations, and then I solve this. Here you will notice H1 conjugate H2 U2, and here you have H2 H1 conjugate U2 minus. So they both will cancel. And this H2 H2, this will also become H2 mod square, like this was H1 mod square. And H1 mod square, H2 mod square, they are what? They are nothing but H mod square. H mod square divided by H, because this will cancel with this. H mod, you will get H mod U1, and this will be a noise which we have to determine its Cn. We have done this many times. For example, we did this for repetition codes. Okay, as was previous example. So we will do it this again. So this is noise. Channel H mod, we will solve this. But if you can, this will be a noise, and you will see in a while that this come out to be Cn 0 and not, complex Gaussian random variable with 0 mean and n not. You will see this after solving. We will do it in steps. And this is H mod U1 for the first. The same thing as he has said, H mod U1. If you take the second column, project this into Y, you will get the R2 or U2. The second output will come out. And this you will do yourself. But we have to show that the noise that is coming is come out to be Cn0 and not. So I just take it to my old notes, just trying to show. So please note, so if there's some mistake, I will try to correct, but I think it is probably right. Remember, we have to show this, that what is the noise statistic of this term. Let's try to do this solve step by step. So H1 conjugate as follows. And we have W1 and W2. So W1 is the noise in the first antenna, W2 is the noise in the second antenna. So a noise in the antenna at the receiver side has both the IQ channels, N0 by N0 by 2. They add up, so you get N0. We have done this many times, so you can see the previous notes. So the second one is W2 conjugate. So yes, I will get Cn0 and not. This is also Cn0 and not conjugate. Now let us solve. Again, we have done this previously for repetition code. Let us try to do this for LMOT. So let us try to solve this. Now what is H1 conjugate? H1 conjugate. H1 is just a channel coefficient. Conjugate means is complex. It's conjugation. This is again we have studied many times, real channel, imaginary channel, J and all that. This comes like this. H2 is again a complex number, simple channel coefficient. And this is again 0 plus n naught, and because of conjugate, it's better that you put a negative sign. No problem. All right, let us go further. Now start multiplying. So this goes with this. This minus j goes with j is j square minus 1 plus 1. This becomes like this. This goes with this. Oh, sorry. This term will go with this minus. And this term will go with this. This will become plus. Again, you can see the next step. This will become plus. Again, this will go this will become plus. This will go with this. This will become minus. And so this will go with this and this. This will be plus, and this will be finally minus plus. Like these terms will be. You will got these terms. Get these terms. Then, and what you can do in this way, that you can take this scalar inside. You know, once you take the scalar inside, it becomes square. So all the scalars inside this becomes square. All right. Minus j is go inside square. All right. Square. Plus j minus j. Actually, you can also take this minus inside. This will become a square. Because this plus or minus negative is irrelevant. Actually, you can convert all of them to plus. This can also become plus. Because minus 1 goes inside, becomes square, it becomes finished. Because it is a variance. Variance doesn't take an effect with positive or negative sign. They can all become plus in this term. Okay? And all become mod square or h square inside. Then what I can do, I cannot combine, right? I will combine all the real noises, all the I noises, and all the Q noises. So I combine all the I noises, in phase noises. So this is in phase, this is all Q phase, this is in phase, 2 in phase, 3 in phase, 4 in phase. I add them, this becomes like this. Add all of the Q phase, it will all become like this. And then what is this? H1, this is H1 mod square, this is H2 mod square, because these are the real imaginary part of H1. And then H1, this becomes H mod square. H mod square can also go inside, it will become H mod square because scalar go inside the H mod square. And then H mod square, this becomes n naught by 2, this becomes n naught by 2. And you combine a real and imaginary, you know how we combine real and imaginary, what we get? The variance is just added and you get Cn0 n naught. So we have proven that the noise statistics for LMOT output is actually n naught. So we have proven that this is n naught. As we in repetition, we are getting the same output. So definitely, depending on the length, H mod is of L length, L diversity gain. So here it is 2 length, you will be getting 2 diversity gain here. So here you can see that you are sending actually 2 different symbols in 2 different slots. But in repetition coding, you are sending one symbol in 2 different slots. So you know it was half. Yeah. So, but with half the power in each symbol. You see the total power is the same in both the cases. You can see LMOT send 2 symbols in 2 symbols. So it is actually sending 2 divided by 2, that is 2. One symbol in one symbol, it is actually saying 1, and diversity is automatically accommodated in LMOT. But in repetition, you have to send 1 symbol in 2 times to get the same diversity gain. You are actually sending 0.5 symbol per symbol time as compared to 1 symbol in symbol time. So we can see that if I assume that both the energies of LMOT and repetition, let us say, are same, then in that case, 2 is simple energy of LMOT is equal to 1 energy symbol of repetition, if their energies are same. But in that energy, you send only 1 symbol, but you are sending 2 symbols. Or even in total 2 symbols, you are sending 1 symbol, but he is sending half a symbol. If the energy you have put the energies of both the systems the same, you are actually taking half of the energy of repetition. If the energy, sending energy is same in both the cases, LMOT is saving 50% of the energy. And again, I've told you transmitted energy is very, very important. Okay, that determines the cost of your link, because the amount of power you send here, that will determine how much energy you receive in the channel after the drop in the channel. Half the power. Okay? Let us look at another angle. So, LMOT scheme can work for any constellation. It can work from PSK, it can work for Palm, it can work for any constellation, it can work. Assume that, let us say it is very simple. We are just using BPSK symbols. So, U1, U2 or U1 conjugate or U2 conjugate, they will be just what? A and minus A. Alright. A combines 1 bit 0, 1, 0, 1. A and minus A, there are only two symbols. So 0, 1, they can cover them. 0 or 1, they can cover their representation. You just need 1 bit for one symbol. So as you know, in LMOT we said we are sending 2 symbols in 2 symbols time. So we are sending actually 2 bits in 2 symbol time, or 1 bit in 1 symbol time. Now, let us bring 4 PAM. Let us bring a repetition scheme. And let's say we say that we are using 4 PAM. So what is 4 PAM? In 4 PAM, you have 4 symbols. You have minus 3B, you have minus B, you have B, you have plus 3B. And what was the average energy of 4 PAM? It was 5B square. What is the average energy of BPSK? It was A square. If let us say B and A are equal, then in that case, this will be 5B square, this will be only B square. Now achieve the same minimum distance as the BPSK symbols, we will be needing 5 times energy, 5B square per symbol. Again, many students were not able to understand previously, so I have again done this in mathematically, so students are able to understand. So please try to observe. So LMOT sends BPSK symbol, that is 2 bits in 2 symbol time, or 1 bit 1 symbol time. We want the same rate for repetition. So we say, all right, use 4 PAM. 4 PAM has 4 symbols. Each symbol has 2 bits. So I will use 2 bits, but they will be repeated in 2 symbol times because there is repetition of double. So 2 bits, 2 symbol, 2 bits or 2 symbols. You are again sending 1 symbol, 1 symbol. So we have kept the rate same. We are keeping the rate same. So the rate is same. So if the rate is same, then what is the advantage of LMOT? Let us check. When you solve the Q and the error function, you will get SNR into H mod square. But what is SNR of PAM? It is 5B square. And what is SNR of that? That is SNR is only A square. So PAM requires 5 into B square, 5 into A square of BPSK. SNR. For the same minimum distance. But PAM is sending 1 symbol, while LMOT is sending 2 symbols for the same rate. Alright. Same minimum distance, you can see that it is 5 times more. Alright. So same data rate. Minimum distance the BPSK with LMOT minimum distance the BPSK with LMOT scheme, we need 5 times energy. If you keep the distance same, yes, I want to keep SNR same. SNR H mod, they determine the distance. I keep the distance same. But if you keep the distance same, you need 5B square. Your SNR is very high. And if I say, all right, no, that PAN sends one symbol while LMOT is sending two BSK symbols. Alright. So because the class, I start the class at 6 o'clock. So I will always finish the class after 75 minutes. But if we miss lectures, then we'll cover those lectures in the rest of the 15 minutes. So that if we have extra lectures. If you have any questions, you can ask. This is just discussion, so we will repeat in the next lecture. So if you have any question, you can ask before we start taking attendances. This last portion, comparison of LMOT with repetition, we will repeat. So, but other things you can ask. If you don't want to ask, then we can, take the attendance. All right, you don't want to ask, so we will take the attendance. So again, I will share you the LMS so that all of you can view. Please turn off your microphones so that everyone can hear. So I will mark your attendances in front of you. Please make sure that all of your microphones are working. So all right, 19 PhD 5.
Present.
1835. So we have 7 attendees, 7 attendees or people who are present. So I will make sure that there are 7. Only 35. 36.
Present, sir.
36 present. Good. 37. 39.
Yes, sir.
42.
Present, sir.
Good. 62. 1862. 1863. 1941.
Present.
1942.
Present.
1943. All right. 1946.
Present, sir.
Thank you very much. 7 remarks. So if you have any questions, you can ask, or we can make this last part. We will be repeating this in the next lecture. So, do you want to ask any questions, or we should refer this to the next lecture?
सर एक तो ये चीज़ है सर हमारी रिकॉर्डिंग्स अवेलेबल नहीं है वो काइंडली जिशान साहब जो है वो देख लें कि वो किस तरह हमें अवेलेबल होंगी लेक्चर रिकॉर्डिंग जो है वो प्ले नहीं होती
अच्छा,
एक चीज़ सर ये है नंबर 2 सर जो पुराने नोट्स भी हैं जो पुराने सर लेक्चर हुए हैं पिछले वीक के सर उसके भी काइंडली वो भी सर अगर आप अपलोड कर दें तो वो अच्छा रहेगा अगर
hey, so they are not uploaded. Let us check. If I share you the
सर आपने आपने शेयर किए हुए हैं, पिछले कुछ हैं, लेकिन सर वो उसमें ना तरतीब नहीं है। जो आपने जो ये नोट्स हैं कोई तरतीब से नहीं है सर। वो मैं समझ नहीं आ रहा है कौन से कहाँ से आगे फॉलो अप हो रहा है। या सर कोई मार्किंग पेपर के ऊपर करके इस तरह कर ले ताकि प्रॉपर से समझ आ जाए।
Hey, I have actually tried to mark them. Let us check if there's because I represent each lecture with a new folder, and then I give pages. So you know, page number they correspond to the higher the page, it will come. For example, here when I have written these 1, 2, 3, 4, 5, 6. So these are the pages. If you just start with a lecture, you can keep the book in front. So you can very well see that I'm moving from one page to another page. So all the pages, they are given in journal. So you will be able to download them. Lecture notes, they are also there. This is the maximum information. I think the main point is, as Salman has pointed, is that you don't have the recorded lectures with you. That is causing the, once you have the recorded lecture, then you can see how am I going from one page to another page. That will not cause any problem. I will be uploading lecture 3 notes also here, so that you today notes are also available. You have no problem. But I will talk to Zishan because I thought that lectures are available. I can see my recorded lectures at my end. So I think that you can also, you just have to go to here post. For example, you go to post, and then let us say, for example, this which happened last Wednesday. If I click this, so you can see this will start playing, and all of this that is we are seeing here, or what we have seen before, that will be repeated in front of you. Just let's have a look. I have not shared the noise, the audio. Just you can do it yourself. I'm just checking that if there is any problem, then we can see. Because I was able to view lectures, and I said that already everything is good. So you can see this was. I can actually hear my audio. You will not be able to hear the audio, but no problem. It is actually running.
बट सर हमें ये वीडियो प्ले नहीं हो रही है हमारे एंड पे।
अच्छा,
सर जो ऑर्गेनाइजर होता है उसके लैपटॉप पे होती है, जो अटेंडी है सर वो उनको पासवर्ड वगैरह या कोड मांगते हैं सर। जब आप माइक्रोसॉफ्ट की स्ट्रीमिंग करते हैं तो वो साइन इन का कोड मांगता है, कहते साइन हो।
चले मैं इसका देख लेता हूँ कि निशान साहब से भी मेरे ख्याल से अगर बैठे ही हैं तो अभी निशान साहब से हम पूछ ही लेते हैं। वो तो मेरे ख्याल से इधर बैठे ही होंगे। कहाँ चले गए? निशान साहब आप इधर हैं? ओ इस्लाम साहब भी हैं। इस्लाम साहब अस्सलाम वालेकुम। इस्लाम साहब अस्सलाम वालेकुम।
वालेकुम अस्सलाम सर, क्या हाल है आपके?
अल्हम्दुलिल्लाह ठीक ठाक है। तो इस्लाम साहब वो बच्चे कह रहे थे कि जो रिकॉर्डेड वीडियो है वो उनके एंड पे नहीं चलेगी, वो मेरे पास तो बड़े आराम से चल जाती है सारी, वो 1.5 घंटे की।
नहीं
तो
सर वो ऐसे है, मैं बताता हूँ उसकी वजह ये है कि वो उनके जो ईमेल एड्रेसेस हैं ना वो यूईटी की नहीं है। तो वो वीडियो उस वक्त प्ले कर सकते हैं कि जो है ना अगर उनके वो जो ईमेल एड्रेसेस यूईटी के होते। तो उसका तरीका ये है सर, आप वो वीडियो डाउनलोड करके ना वहां से आप उनके साथ वैसे शेयर कर दें या उसको दोबारा से जो है किसी तरह से डाल दें।
अच्छा,
हाँ जी।
तो इनको यूईटी के अकाउंट्स नहीं किए जाएंगे? यूईटी के अकाउंट्स
नहीं सर, ये जो एडेड है ना, स्टूडेंट्स एडेड है आपके अकाउंट में, ये इनके अपने पर्सनल लगी ईमेल अकाउंट्स हैं, उन अकाउंट से एडेड है।
अच्छा,
ये यूईटी वाले तो पता नहीं इनके बने तो हुए हैं, पता नहीं लेकिन ये यूज करते हैं या नहीं करते, क्या सिलसिला।
अच्छा बने तो हुए, तो इनसे मैं कहूँ भी आप उससे लॉग इन कर लें, ऐसे नहीं हो सकता?
नहीं, उसको फिर वो ऐड करना पड़ेगा ना उनको।
अच्छा, सारा कुछ चेंज हो जाएगा।
बिल्कुल।
ऐसे वो मैं चाहता नहीं था कि लेक्चर ना बाहर की तरह जाए ना।
चलें सर, अभी इस तरह है ना कि अभी आप इसको इनको जो है ना अभी तो चलने देना, फिर अभी कुछ दिनों में देखते हैं इसको, कोई और सिलसिला ढूंढते हैं हम इनको यूटी के अकाउंट से ऐड करने की कोशिश करते हैं इनको।
ठीक है चलो ठीक है
हाँ जी।
सर, बहुत बहुत शुक्रिया, थैंक यू
ओके सर।
Thank you. So I have talked to Mr. Islam